A cold, dark, and empty cosmos awaits us in the far future. This is not a story from a movie, but a real scientific forecast for the final fate of the universe. Understanding how everything ends is one of the most profound journeys we can take, forcing us to face the temporary nature of all existence. By the end of this, you will grasp the leading scientific theories for the end of everything, from a violent rip in space-time to a silent, frozen equilibrium. We will uncover whether a mysterious force is stretching our reality to its breaking point, and what happens when the last black hole evaporates. What does a universe with an expiration date mean for you, right here and now? That simple image of rising raisin bread gives us a powerful way to visualize our expanding reality. As the dough stretches, every raisin, every galaxy, moves away from every other. This was the stunning revelation from astronomer Edwin Hubble in the 1920s, a discovery that shattered the old idea of a static, unchanging cosmos and revealed a universe in motion. But what force is driving this expansion, and more importantly, why is it speeding up? The answer points to the most mysterious ingredient in the cosmic recipe, an entity we call dark energy. Think of the universe as a perpetual tug of war. On one side, you have gravity pulling everything together, trying to collapse the cosmos back in on itself. On the other side, you have dark energy, a mysterious pressure embedded in the fabric of space itself, pushing everything apart. For billions of years, this battle was relatively balanced. But then, around 5 billion years ago, something shifted. Dark energy gained the upper hand. The expansion of the universe didn't just continue, it began to accelerate. This discovery was so revolutionary it earned the Nobel Prize in Physics in 2011. We measure this accelerating rate with a number called the Hubble constant, though constant is a bit of a misnomer, as the rate itself is changing over time. This acceleration is not just a minor detail, it is the central plot point in the story of our universe's end. To truly understand the finale, we must rewind the cosmic tape all the way back to the very first moment. That newborn universe was a cauldron of almost unimaginable energy. In its first fleeting moments, the cosmos was so hot and dense that the forces governing reality, like gravity and electromagnetism, were fused into a single, unified power. This was not a conventional explosion flinging debris into a void, but the very fabric of space-time stretching and cooling at a phenomenal rate. From that primordial state, everything we know was born, and the precise conditions of that birth wrote the first draft of our cosmic end. The amount of matter and energy created, the specific geometry of space, these were not random. They were the initial settings, the fundamental parameters that would dictate the entire future of reality. The renowned physicist Stephen Hawking pondered this profound fine-tuning, suggesting that even a minuscule change in these initial conditions would have resulted in a universe that collapsed instantly or flew apart so rapidly that no stars, planets, or life could ever form. We are here only because the numbers lined up perfectly. We have a snapshot of this infancy, a faint afterglow that permeates all of space known as the cosmic microwave background. This radiation is the cooled remnant of the Big Bang's fiery light, a baby picture of the cosmos when it was just 380,000 years old. By studying this ancient echo, scientists can measure the universe's vital signs with incredible accuracy. They can read the precise balance between the outward push driven by dark energy and the inward pull of all matter, both the visible kind and the mysterious dark matter. For billions of years, this tug of war defined the cosmos. But the initial conditions set by the Big Bang guaranteed this balance would not last. The scales were always destined to tip, leading us directly to the first and most haunting forecast for the end of all things. That silent, motionless state is the most widely accepted forecast for our cosmic future, known as the heat death or the Big Freeze. Picture the very last star in the universe, a faint red dwarf, finally burning through its fuel. Its light winks out, plunging its planetary system into permanent darkness. This is not an isolated event, but the final act in a cosmic play that has been running for trillions of years. One by one, all stars, from the brilliant blue giants to the humble suns like our own, will exhaust their nuclear fuel and die. What remains is a vast, expanding graveyard of cold, dead stellar remnants, neutron stars and black holes, all drifting further and further apart in an ever-cooling void. The engine driving this slow, inexorable decay is the second law of thermodynamics. This fundamental rule of physics tells us that entropy, a measure of disorder, always increases in an isolated system. Think of a hot cup of coffee left on a table. It doesn't stay hot, it naturally cools down as its heat spreads out into the room, moving toward a state of uniform temperature, a state of higher entropy. The entire universe is that isolated system on the grandest possible scale. Right now, we have pockets of high energy like stars and vast regions of cold, empty space. This difference in energy allows for work to be done, for stars to shine and life to exist. But as the universe expands and evolves, these energy differences slowly even out. The cosmos is progressing toward a state of maximum entropy, where energy is spread perfectly thin and uniformly across the entire expanse of spacetime. In this final equilibrium, the temperature everywhere approaches absolute zero, the point where all molecular motion ceases. There are no more hot spots or cold spots. No energy can be extracted to power any process, not a star's fusion, not a planet's weather, not a single thought. The universe becomes a static, lukewarm soup of fundamental particles, where nothing ever happens again forever. The Victorian physicist Lord Kelvin was one of the first to grasp the terrifying implications of this thermodynamic end for a solitary cosmos. His ideas have been refined with our modern understanding of an expanding universe, but the core principle remains chillingly intact. Galaxies will be pulled so far apart by dark energy that they will vanish over each other's cosmic horizons. The universe will not end with a bang, but with the slow, final sigh of a system that has simply run out of usable energy, like a clock whose springs have fully unwound, destined to sit in perfect, eternal stillness. Yet, as quiet as this end may seem, another theory proposes a finale of shocking speed and violence. But the Big Freeze is not the only possible finale. There exists a far more violent and immediate end, a theory where the fabric of reality is torn to shreds in a final, frantic moment. This is the Big Rip. It all depends on the true nature of the dark energy that currently accelerates the universe's expansion. What if dark energy is not constant but grows stronger over time? This hypothetical extreme form is known as phantom energy. Think of dark energy not as a steady push, but as a pressure that intensifies relentlessly, its repulsive gravity becoming more powerful with every passing second. For billions of years, the universe would appear to expand normally, but the phantom energy would be silently accumulating its strength. The end would come with shocking speed. First, the phantom energy's grip would overcome the gravitational glue holding galaxy clusters together. These vast islands of stars would be flung apart into the void. Next, the force would shred individual galaxies. The Milky Way, along with all its neighbors, would be pulled into stellar confetti. Then it would target the stars themselves. The phantom energy's pull would become stronger than the gravity holding a star together, and suns would be violently disassembled. Planets would be ripped from their orbits and torn apart. In the final, unimaginable moments, the repulsive force would exceed the very nuclear forces that bind atoms together. Every molecule, every atom, every proton and neutron would be shredded into its fundamental components. The universe would end not with a whimper, but with a sudden, total dissolution of spacetime itself, leaving behind a meaningless sea of disconnected particles. This concept was formally calculated by physicists Robert Caldwell, Mark Kamiankowski, and Nevin Weinberg, who mapped the conditions for such a catastrophic divorce of reality. One day, everything would seem normal. The next, the cosmos would be gone. Yet, as terrifying as this explosive end may be, it forces us to confront an even more profound possibility. What if the end is not truly an end at all, but a prelude to a brand new beginning? There was a time when scientists believed the cosmos would eventually reverse its great flight. Instead of fading into a cold, dark stillness, the universe could halt its expansion and begin to fall back in on itself. This is the theory of the Big Crunch, a dramatic finale that is the mirror image of the Big Bang. Picture the last galaxies not drifting apart but turning back, drawn together by the relentless pull of gravity. Over billions of years, this cosmic contraction would accelerate. The vast, empty voids of space would shrink. Galaxies would begin to merge and collide, their stars packed into an ever tighter volume. The background temperature of the universe, now just a few degrees above absolute zero, would begin to climb. The night sky would grow brighter and hotter as the cosmos itself becomes a colossal furnace. This inward rush would culminate in a single point of unimaginable density and heat, a singularity, crushing all the universe's matter and energy back into a state from which it originally emerged. For this to happen, the density of matter in the universe would need to be high enough for gravity to eventually overcome the outward momentum of the Big Bang. It was once the leading model for our cosmic fate, offering a kind of symmetry, a beautiful and complete story with a clear beginning and a definitive end. Yet this story might not be final. Some of the greatest minds in physics, like John Archibald Wheeler, pondered an even more incredible possibility. What if the Big Crunch is not an end at all, but a cosmic reset button? In this cyclic model of the universe, each Big Crunch immediately triggers a new Big Bang, birthing a fresh cosmos from the ashes of the old one. Our universe would be just one turn in an endless, breathing cycle of creation and destruction, a phoenix rising from its own demise over and over for all eternity. Wheeler even speculated that with each new cycle, the fundamental laws of physics might be randomly shuffled. In one cycle, gravity could be stronger, creating a universe of brief, violent stars. In another, the nuclear forces might be weaker, preventing atoms from ever forming. This cyclical universe becomes a factory for reality, generating a multiverse of possibilities across infinite time. For this poetic vision to be true, the dark energy currently accelerating the expansion would have to be a temporary force, a cosmic phase that eventually fades and allows gravity to take command once more. However, our current observations of the universe's accelerating expansion suggest that dark energy is a permanent fixture, making the prospect of a Big Crunch appear increasingly unlikely. It seems the universe is set on a path of perpetual expansion, but that very expansion might lead to a fate even stranger than collapse, born from the bizarre rules that govern the smallest scales of existence. Our universe may be sitting on a precarious ledge, a temporary state of existence that could vanish in an instant. This is the theory of vacuum decay, a catastrophe born from the strange rules of quantum physics. To understand it, picture a landscape of hills and valleys where the height represents energy. Our entire cosmos might currently be resting in a false vacuum, a high-energy valley that seems stable but is not the lowest possible state. A truer, more stable vacuum could exist at a much lower energy level, like a deeper valley just over a hill. The terrifying possibility is that our universe could suddenly tunnel through that hill, transitioning to the true vacuum without any warning. This event would not be a conventional explosion. It would begin at a single point in space, perhaps triggered by a random quantum fluctuation or even a high-energy particle collision in an experiment. A bubble of this new, true vacuum would instantly form and begin expanding in all directions at the speed of light. The wall of this bubble would be a boundary where the fundamental laws of physics, as we know them, cease to exist. Inside the bubble, the very constants of nature, like the strength of gravity or the mass of an electron, would be rewritten. The new laws would be so alien that structures like atoms and molecules could not hold together. Chemistry, the basis for all matter and life, would be impossible. The bubble would expand at light speed, meaning we could never see it coming. One moment, the universe is normal. The next, a wave of new physics sweeps through our solar system, silently and instantly dissolving every star, planet, and living thing into a formless state governed by entirely different rules. The cosmos we knew would be erased, not with fire or ice, but with a quiet and absolute redefinition of reality itself. Stephen Hawking and other physicists have pointed out that our universe's apparent stability is no guarantee of its eternal safety. This theory introduces a profound unpredictability into the cosmic endgame, a reminder that the end could be lurking in the quantum noise of the next second. Yet, while these grand theories foretell the fate of the entire cosmos, the destiny of the individual structures within it, like our own galaxy, tells its own compelling story. Our own galactic neighborhood is headed for a spectacular collision. The Milky Way and its great spiral neighbor, Andromeda, are locked in a gravitational dance destined to merge in about 4 billion years. They will not crash through one another like wrecking balls, but rather perform a slow cosmic ballet, their stars weaving together over billions of years to form a single, enormous elliptical galaxy that astronomers have nicknamed Milkdromeda. Our entire local group of galaxies will eventually coalesce into this one colossal island of stars. Yet, even as this great merger concludes, a profound isolation will set in. The same dark energy that drives the universe's expansion will stretch the fabric of space so drastically that it will overwhelm the gravitational glue holding the largest structures together. The great chains and walls of galaxy clusters, the superclusters we map today, will be torn apart. One by one, every other galaxy cluster beyond our own local group will be pulled away over the cosmic horizon, their light stretching into oblivion. Imagine a ship in the middle of an ocean that is growing faster than any vessel can sail. The other ships first become distant specks, then vanish entirely beyond a horizon you can never cross. For the future inhabitants of Milkdromeda, this will be their permanent reality. In roughly 100 billion years, an astronomer looking out from this merged galaxy would see a sky devoid of any other galaxies. The night sky, which for us is filled with the faint, fuzzy light of distant island universes, would be utterly black. All the evidence we take for granted today would be gone. The redshift of fleeing galaxies, the very observation that revealed our expanding universe, would be impossible to see. Even the cosmic microwave background, the faded glow of the Big Bang, would have redshifted to such long wavelengths that it would be undetectable, its energy dissipated into a near-perfect vacuum. Future scientists would have no reason to believe in a cosmic beginning or a vast, expanding cosmos. they would conclude they live in a static, self-contained island universe with no knowledge of the grand, dynamic history we are privileged to witness. Their cosmos would be their galaxy and nothing more, a solitary island in an eternal, impenetrable dark. And within that final, lonely galaxy, the long process of stellar decay will already be well underway as the last stars begin their long, slow fade into darkness. The final stars are living on borrowed time. Across the cosmos, the great stellar nurseries have already fallen silent, their reservoirs of hydrogen and helium gas either consumed or scattered so thinly by the universe's expansion that new stars can no longer ignite. The grand, sparkling spiral of Milkdromda is now a gallery of dying embers. The brilliant, massive stars were the first to go, exploding in supernova after just a few million years of glory. Our own sun and stars like it will last for billions of years before swelling into red giants and then shedding their outer layers, leaving behind their dense, Earth-sized cores as white dwarfs. These white dwarfs will glow with residual heat for trillions of years, a faint, fading warmth in the growing cosmic chill. But the true marathon runners of the stellar world are the red dwarfs. These small, dim stars are so frugal with their nuclear fuel that they can shine for trillions, even tens of trillions of years. They will be the last sources of warmth and light in the galaxy, the final sentinels of an age that was once ablaze with suns. But even their immense lifespan has an end. One by one, they too will exhaust their fuel, cooling and darkening until they become cold, black spheres of degenerate matter known as black dwarfs. A black dwarf is the final, ghostly corpse of a star, a crystallized cinder so cold that it emits no light at all. The last flicker of nuclear fusion in the universe will cease. This moment marks the official end of the stelliferous era, the age of stars that we are so fortunate to live in. What follows is an epoch of almost unimaginable duration called the degenerate era. The universe becomes a far darker and quieter place. The primary sources of light will no longer be the steady glow of suns, but rare, sporadic events. Occasionally, the slow gravitational dance of two dead stars, like brown dwarfs or white dwarfs, will bring them close enough to collide, creating a brief, brilliant flash of light in the eternal darkness. The remaining structures in this dark age are the compact, exotic remnants of stellar evolution. Space will be populated by these dark, dense objects, neutron stars, the unimaginably dense cores left behind by supernova, and black dwarfs, the cold remains of stars like our sun. And for a time, the black holes will reign, growing slowly as they feed on the sparse, dark matter that still drifts through the void. But in this new era, even the mightiest objects are not eternal. Their fates are governed by a strange and subtle quantum whisper, a process that will ultimately unravel the last vestiges of structure in the cosmos. Black holes will inherit this dark and silent cosmos. Long after the last star has faded, these gravitational monsters will become the universe's final landmarks. This is the black hole era, a period of staggering duration where gravity holds its final dominion. Across the vast expanse of the galaxy, stellar mass black holes, the remains of massive stars, will drift through the void. At the center of what was once Milkdromda, the supermassive black hole that once anchored our galaxy will still loom, a dark titan in an empty throne room. Their power is absolute, yet their reign will be one of profound stillness. Their activity is measured not in years but in epochs. The occasional whisper of a black dwarf or a wisp of dark matter straying too close will be drawn in, creating a faint flash of X-rays as it crosses the event horizon. These will be the rarest of cosmic events, brief sparks in an ocean of darkness, separated by millions or even billions of years of absolute quiet. But even these mighty rulers are not eternal. They face a slow, insidious decay from within, a process that challenges our very understanding of their nature. This is Hawking radiation, a brilliant theoretical discovery by Stephen Hawking. He realized that the vacuum of space is not truly empty. It is a seething foam of virtual particles, pairs of matter and antimatter that constantly pop into existence and then annihilate each other. At the very edge of a black hole's event horizon, the point of no return, something strange can happen. One of these virtual particles might fall in while its partner escapes. From the outside, it looks as if the black hole has emitted a particle. To conserve energy, the black hole must pay for this emission by losing a tiny, tiny amount of its own mass. This is an excruciatingly slow process. A black hole with the mass of our Sun would take longer than the current age of the universe to evaporate significantly. But in a cosmos where time has lost all meaning, even the mightiest structures will eventually succumb. As a black hole loses mass, the process subtly accelerates. In its final moments, it is theorized to vanish in a sudden, brilliant flash of high-energy particles and radiation, a final shout in the silent dark. The largest supermassive black holes, those weighing billions of times our Sun, could take a googol years to evaporate. That is the number 1 followed by 100 zeros, a time span so vast it defies all human comprehension. For nearly all of that unimaginable duration, these black holes will be the last bastions of significant structure, the final objects that release any meaningful energy into the cosmos. Their eventual disappearance marks the end of an era defined by gravity and structure, and the beginning of the universe's true final act. The final black hole has evaporated. With its last flash of gamma rays, the last object with any meaningful structure vanishes from reality. We now enter a phase of the cosmos so profoundly ancient and empty that it defies all human intuition, the Dark Era. In this epoch, the very bedrock of the material world begins to crumble. The protons and neutrons that form the heart of every atom, the very building blocks of all we see and touch, are not necessarily eternal. Many of our most ambitious theories of physics, the grand unified theories that attempt to describe the fundamental forces, predict that protons themselves should decay. We have never observed this happening, which tells us that if it does occur, a single proton must have a staggeringly long lifespan, perhaps 10 to the 34 years or more. A time span so long that it makes the entire previous history of the universe seem like a single blink in an endless night. But in the Dark Era, even these immense timescales have finally elapsed. Imagine the cold, dark cinder of a black dwarf star, a star corpse that has drifted in perfect darkness for eons. It is still made of atoms of atomic nuclei. But as proton decay begins, this stability ends. One by one, the protons inside these ancient remnants spontaneously transform, breaking down into lighter particles like positrons and photons. It is a process not of burning or explosion, but of quiet, fundamental dissolution. The black dwarf does not shatter, it simply fades. Its matter unmakes itself, dissolving into a faint, ethereal glow of radiation. Every planet, every asteroid, every speck of cosmic dust that somehow survived the previous eras will suffer the same fate. All complex matter, every structure that was ever built from atoms, will eventually cease to exist. What remains is a universe transformed into an ultra-diffuse, ever-expanding soup. This final state is a sea of the most basic particles, a thin gas of electrons, positrons, neutrinos, and photons, all swimming in a background of dark matter, which, as far as we know, remains stable and unaffected. There are no more clumps, no more lumps of matter, no more places for anything to happen. gravity, the force that once sculpted galaxies and stars, has lost all its anchors. With no massive objects left, there is nothing for it to pull together. The cosmos becomes a perfectly uniform, incredibly thin bath of energy and particles, cooling and stretching toward an absolute equilibrium. In this dark era, the very concept of an object, of a thing, becomes meaningless. The universe is a featureless void in its final state, a canvas with no paint left upon it. Yet, even in this ultimate stillness, the strange rules of quantum mechanics suggest that the story may not be completely over. The universe has become a silent, featureless expanse, a near-perfect vacuum where the very notion of time begins to lose its meaning. Yet, within this ultimate stillness, the strange rules of quantum mechanics whisper that nothing is ever truly final. In a cosmos that persists for a near-infinite duration, the impossible becomes not just possible, but statistically inevitable. This bizarre possibility is captured in a thought experiment known as the Boltzmann Brane. Imagine a universe so vast and ancient that a random quantum fluctuation could, by sheer chance, spontaneously assemble a fully formed, conscious brain out of the surrounding particle soup. This brain would pop into existence, complete with false memories of a past life, a world, a universe that never truly existed. It would experience a single, fleeting moment of consciousness before dissolving back into the chaos from which it came. This unsettling idea stems from the work of the 19th century physicist Ludwig Boltzmann, who linked the concept of entropy to probability. He understood that a system in a state of high entropy, like our cold, end-stage universe, is not perfectly uniform. There are always tiny, random fluctuations. In a box of gas, atoms might randomly cluster in one corner for an instant, creating a pocket of order before dispersing. In an eternal, high-entropy universe, these fluctuations can, given enough time, produce any configuration of matter, no matter how complex. The spontaneous formation of a single, conscious brain is astronomically more probable than the gradual, organized evolution of an entire universe filled with observers like us. This creates a profound philosophical paradox. Which scenario is more likely? That we are ordinary observers living in the relatively ordered early history of the cosmos, or that we are incredibly rare, momentary fluctuations in a much older, dead universe, merely dreaming of a past that never was? The possibility of Boltzmann branes forces us to confront the nature of observation, reality, and the arrow of time in a cosmos that has lost all structure. While this remains a highly speculative frontier of cosmology, it highlights the ultimate limits of predictability and our understanding of existence itself. To move from these dizzying theoretical extremes and determine the actual fate awaiting our universe, we must turn from pure thought to the hard, observational evidence written across our night sky. Dark energy is the silent architect of our cosmic fate, a sculptor whose unknown properties are carving the final shape of reality. Its discovery in 1998 was a complete shock to the scientific community. Astronomers were observing distant supernova, expecting to measure how much the universe's expansion was slowing down due to gravity. Instead, they found the opposite. The most distant stellar explosions were fainter than predicted, meaning they were farther away than they should have been. The expansion of the universe was not slowing, it was speeding up. This revelation pointed to the existence of a mysterious, repulsive force woven into the fabric of space itself, a force we named dark energy. The true nature of this force is the central mystery that will determine our final destiny. Is it a constant, unchanging energy inherent to the vacuum of space, which Albert Einstein once called the cosmological constant? Or is it something dynamic, a cosmic field that evolves over time, which physicists refer to as quintessence? The answer lies in a critical number known as the equation of state parameter, simply called W. Think of W as the identity card for dark energy. If W is exactly -1, dark energy is a stable, constant force. The universe will continue its accelerated expansion forever, leading inevitably to the long, cold fade of the heat death. But if W is less than -1, dark energy is something far more exotic and terrifying, a phantom energy that grows stronger over time. This is the path that ends in the violent disintegration of the Big Rip. Current data from powerful observatories like the Planck satellite meticulously map the cosmic microwave background, and they tell us that W is incredibly close to -1. The evidence strongly points toward the slow, frozen end. Yet, the measurements are not perfect. The error bars on that number still hold a sliver of possibility for a different, more dramatic finale. This tiny uncertainty is why the quest to understand dark energy is one of the most urgent missions in modern cosmology. Giant new telescopes and space missions are being designed with one primary goal: to measure the expansion history of the universe with unprecedented precision, to finally read the identity card of this cosmic architect and learn the true expiration date written into the laws of physics. These cosmic time machines are not built of gleaming metal, but of mathematics and light. When an astronomer points a telescope like Hubble or the James Webb into the depths of space, they are not just looking across distance, they are looking back in time. The light from a galaxy 10 billion light-years away has been traveling for 10 billion years to reach us, showing us the universe as it was in its youth. By comparing this ancient light to the light from nearby galaxies, we can measure how the expansion rate has changed over cosmic history. The key is to find a reliable cosmic milepost, a signpost whose true brightness we know. This is where Type Ia supernova becomes so crucial. These are not just any stellar explosions, they are the detonations of white dwarf stars that reach a specific critical mass. Because this trigger point is always the same, the resulting explosion always shines with a known, intrinsic brightness. Think of it as finding a 100-watt light bulb in a vast, dark field. By measuring how dim it appears from your vantage point, you can calculate exactly how far away it is. When astronomers did this in the late 1990s, they expected to see these distant standard candles looking relatively bright, indicating the universe's expansion was slowing down. Instead, they were faint. They were farther away than anyone had predicted. It was as if a car, instead of slowing down as it coasted uphill, was mysteriously pressing harder on the accelerator. This was the direct, observational proof that dark energy was real, and that it was winning the cosmic tug of war. But to confirm this finding and peer even deeper into the past, scientists use another, even older fossil of the universe's birth. The cosmic microwave background is the cooled remnant of the Big Bang's first light, a snapshot of the cosmos when it was a mere 380,000 years old. By mapping the tiny temperature fluctuations in this afterglow with incredible precision, missions like the Planck satellite could measure the universe's vital signs at its infancy. They could read the precise balance of matter, radiation, and dark energy written into the fabric of the young cosmos. This baby picture tells us the initial conditions, the starting point from which everything else unfolded. To trace the story from that starting point to the present day, astronomers have developed another ingenious cosmic ruler, one etched into the very distribution of galaxies. In the first moments after the Big Bang, the universe was a seething, hot plasma, with pressure waves racing through it like sound moving through air. When the cosmos cooled enough for atoms to form, these waves froze in place, leaving a faint, preferred scale imprinted on the distribution of matter. This imprint, known as Baryon acoustic oscillations, acts like a standard ruler etched across the sky. By measuring the apparent size of this ruler at different distances, and thus different eras, we can see how the stretching of space has warped our perception of its length over billions of years. It is like having a measuring tape that was woven into the universe at its birth, allowing us to see how much that tape has been stretched over time. Today, ambitious projects are combining all these methods to corner dark energy. The Dark Energy Survey has already mapped millions of galaxies, while the upcoming Euclid and Roman space telescopes will create three-dimensional maps of the cosmos on a scale never before attempted. They will measure the shapes and distances of billions of galaxies, watching how the gravity of dark matter and the push of dark energy have sculpted the large-scale structure of the universe over cosmic time. Each supernova, each frozen sound wave, each distorted galaxy is a single data point in the ultimate forensic report. By combining them, scientists can finally pin down the properties of dark energy, that critical W parameter, and rule out entire classes of cosmic endings. The data streaming down from these observatories is not just abstract science, it is a live feed from the front lines of cosmic destiny, a message in a bottle that tells us how the story of everything will finally conclude. And as with any great mystery, the final chapter may still hold surprises that rewrite the entire plot. This staggering discrepancy points to one of the most profound mysteries in all of science. The vacuum of space, according to our best theories of the quantum world, should be a raging ocean of energy. Every cubic centimeter of so-called empty space should be teeming with a colossal background energy, a consequence of virtual particles flickering in and out of existence. When physicists calculate the strength of this vacuum energy, the number they get is astronomically huge. Yet, when astronomers measure the actual effect of this energy on the expansion of the universe, what we call dark energy, the value is almost zero. It is not perfectly zero, but it is 1 followed by 120 zeros times smaller than the prediction. This is not a small error. It is the single greatest failure of a theoretical prediction in the entire history of physics. This is the cosmological constant problem, a gaping hole in our understanding that screams we are missing something fundamental. How can the theoretical expectation and the observational reality be so catastrophically different? This puzzle forces us to confront a deep rift between our two most powerful descriptions of reality: Einstein's theory of general relativity, which governs the vast cosmos of galaxies and black holes, and quantum mechanics, which rules the tiny realm of atoms and particles, are fundamentally at odds here. They cannot both be right in their current forms when it comes to the energy of empty space. This suggests a deeper theory must be waiting to be discovered, a theory of quantum gravity that would unite these two pillars of physics and perhaps resolve this monstrous discrepancy. The fact that the observed value is not zero, but is instead a tiny, precise number that allows for our existence, is what physicist Steven Weinberg found so telling. He explored the anthropic principle, the idea that the universe we observe must have the properties that allow for conscious life to arise within it. If the cosmological constant were even slightly larger, its repulsive force would have torn the universe apart before the first stars could ever form. No stars, no planets, no observers. In a multiverse of countless universes, each with different physical constants, we naturally find ourselves in one of the rare, finely tuned ones where the numbers just barely allow for galaxies and life. This delicate balance is the very bedrock of our long-term forecast. The entire scenario of the heat death, that slow, cold fade into equilibrium, rests on one critical assumption: that the dark energy driving the acceleration is a true constant, unchanging for all time. But what if our deepest mystery is a clue that this assumption is wrong? What if the cosmological constant is not constant at all? Our cosmic fate hinges on a single, fragile number. The equation of state parameter W is the signature of dark energy, and its value is the difference between a slow, cold farewell and a sudden, violent end. If this number is less than -1, we are not just dealing with a steady push, but with a force that grows stronger and denser as the universe expands. This hypothetical substance is known as phantom energy, and its existence would trigger the most dramatic finale of all, the Big Rip. Think of phantom energy not as a constant wind, but as a storm that gathers strength the more space it has to grow. Its repulsive gravity would intensify over time, creating a terrifying positive feedback loop. The more the universe expands, the stronger the phantom energy becomes, and the stronger it becomes, the faster it forces the universe to expand. This runaway process would send the scale factor of the universe, the measure of its size, racing toward infinity in a finite amount of time. It is a universe becoming increasingly unstable the larger it gets, destined to tear itself to pieces from the inside out. The timeline for such a catastrophe is not indefinite. If phantom energy is real, scientists have calculated that the end could come in as little as 22 billion years from now. The final moments would be a spectacle of destruction unfolding faster than the speed of light. First, the phantom energy's grip would overcome the gravitational glue holding galaxy clusters together, flinging them into the void. Then, individual galaxies like our own Milkdromda would be shredded into stellar confetti. Next, the force would rip stars apart, their nuclear furnaces extinguished as the phantom energy overwhelms the gravity that holds them together. Planets would be torn from their orbits and vaporized. In the last fraction of a second, the repulsive force would exceed the very nuclear forces that bind atoms together. Every molecule, every atom, every proton and neutron would be violently dissociated into a meaningless spray of fundamental particles. The fabric of spacetime itself would be torn asunder, leaving behind a cosmos that is not cold or dark, but simply undefined. This is a future where the universe does not just run out of energy, but where the very laws that allow for structure are revoked. While current data from the Planck satellite and other observatories strongly suggests that W is very close to -1, favoring the long freeze, the error bars on that measurement have not entirely slammed the door on this phantom menace. The search for any tiny variation in dark energy's strength over time is in essence a hunt for evidence of this cosmic instability. The discovery of such a variation would be a monumental shift in our understanding, rewriting the final chapter of everything from a slow elegy to a sudden, explosive finale. Yet, even as we contemplate the end of our entire cosmic bubble, a grander possibility emerges. What if this catastrophic dissolution is not the end of everything, but merely the end of our local reality? Our universe could be just one temporary bubble in an infinite cosmic foam. This is the Multiverse Hypothesis, a vision of reality where the entirety of our history, from the Big Bang to its final fate, is just a local event within a much grander, eternal meta-cosmos. Picture a pot of water on a rolling boil. Bubbles of steam form, expand, and pop on the surface. In this analogy, our entire observable universe is one such bubble, nucleating out of a seething, background energy field known as the false vacuum. This process, called eternal inflation, was pioneered by physicists like Alan Guth and Andre Linde. It suggests that the rapid inflationary expansion that shaped our early universe never truly stopped everywhere. It continues in the background, a roiling sea of spacetime that constantly spawns new baby universes, each pinching off into its own separate reality with its own unique set of physical laws. In this staggering picture, beginnings and endings are commonplace. One daughter universe might form with so much matter that it rapidly collapses back into a big crunch. Another might be born with a dominant form of phantom energy, dooming it to an early big rip. Ours, with its specific balance, seems headed for a long heat death. Our universe's physical constants, the very numbers that dictate the strength of gravity and the mass of an electron, may not be finely tuned miracles. They could simply be a random draw from a cosmic lottery, one possible combination out of a near-infinite distribution. This is where the anthropic principle finds a powerful home. If countless universes exist with every conceivable set of physical laws, then it is no surprise that we find ourselves in one of the rare, habitable ones. We are not here because the universe was designed for life. We are here because in a vast multiverse of mostly dead and empty realities, a few will, by pure chance, have the right conditions to spawn observers. This framework completely transforms the question of our ultimate fate. The end of our universe is no longer the end of everything. It is a relative event specific to our pocket of reality. While our stars fade and our particles dissolve into a cold equilibrium, the greater multiverse continues its endless creative churn, giving birth to new cosmic stories we will never see. This expansive view challenges our most basic assumption, forcing us to ask not how the universe will end, but what we even mean by the universe in the first place. The relentless increase of entropy is the engine driving time's arrow forward. We remember the past but not the future because the past was a state of lower disorder, a more organized arrangement of the universe's energy. This one-way street from order to chaos is codified in the second law of thermodynamics, and its starting point was the incredibly low entropy state of the Big Bang. Physicist Sean Carroll uses a powerful analogy to explain this. Think of a jar of ink and a jar of water. If you pour the ink into the water, it will naturally spread out and mix, creating a uniform purple liquid. This is the high entropy state, the final equilibrium. You would never expect the mixed liquid to spontaneously separate back into a jar of pure ink and a jar of pure water. The early universe was like that pristine, separated state, a highly ordered configuration that has been mixing and spreading out ever since. Our entire experience of cause and effect, of memory and aging, is a direct consequence of our position on this cosmic slope from order to disorder. We are carried along by the current, always moving toward greater chaos. But what happens when we reach the bottom of this hill? In the final state of the heat death, the universe achieves maximum entropy. Energy is perfectly and uniformly spread across an infinite, cold void. There are no hot stars to contrast with cold space, no ordered structures to break the perfect symmetry. In this ultimate equilibrium, no processes can occur, nothing changes, and if nothing changes, if no events can distinguish one moment from the next, then the very concept of time as a flowing river loses all meaning. The arrow of time, which has flown for billions of years, simply vanishes. There is no past or future, only an endless, featureless present. This erasure of time's direction raises dizzying questions about the nature of reality itself. Our consciousness, our memories, our very sense of self are processes that rely on this temporal gradient. In a timeless universe, what would it mean to think or to be? As we confront this ultimate stillness, we are forced to ask a more immediate question. Could any form of life, any intelligence, possibly survive long enough to witness the fading of time's arrow? Even the most advanced civilization will face an ultimate energy famine. Far in the future, a society of conscious beings might huddle around the last evaporating black holes, using the faint Hawking radiation as their final power source. They would have engineered their own existence down to the most minimal level, slowing their thoughts to match the cooling of the cosmos. The physicist Freeman Dyson envisioned such a possibility, where life could stretch a finite supply of energy over an infinite subjective time by reducing its metabolic rate to a near standstill. In this slowed state, a single thought might span millions of years, creating a perceived eternity from the universe's last gasps. Yet this poetic vision crashes against a fundamental wall, the absolute limit imposed by the heat death. When the universe reaches maximum entropy, no free energy remains. There are no temperature differences, no energy gradients to exploit. At that point, no work can be done and no information can be processed. All computation, the very basis of thought and consciousness, must grind to a permanent halt. This final state implies our cosmos has a finite information capacity, a total amount of knowledge that can ever be learned, processed, or remembered throughout all of cosmic history. The ultimate struggle for intelligence would not be against other species, but against the entropic decay of reality itself. It becomes a grand cosmological engineering project, a desperate race to harness every last joule of usable energy before the lights go out for good. Is this our inescapable fate, or could a sufficiently advanced intelligence find a loophole in the laws of physics and escape this dying universe entirely? The ultimate act of cosmic engineering would be to build a new reality from the ashes of the old. A civilization that has mastered the energy of its entire galaxy might not resign itself to the long freeze. Instead, it could attempt the unthinkable, creating a stable wormhole to another universe or triggering the birth of a new cosmos in a laboratory. Such a feat would require manipulating the fabric of space-time at the most fundamental level, harnessing energies near the Planck scale, where the classical laws of gravity break down and quantum foam reigns. This is not engineering as we know it. It is the manipulation of reality's source code, a project that would make the construction of Dyson spheres seem like child's play. One of the most profound ideas in this domain comes from physicist Lee Smolin, who proposed a form of cosmic natural selection. In his theory, every black hole could be the seed for a new Big Bang, giving birth to a daughter universe with physical constants slightly different from its parent. Universes that produce many black holes would, in turn, produce more offspring, creating a multiverse where the laws of physics evolve to favor black hole production. If such a mechanism exists, a sufficiently advanced intelligence might learn to catalyze it. They could engineer the conditions to create black holes deliberately, not for power but for procreation, spawning a lineage of new universes. In this breathtaking vision, intelligence becomes a trans-cosmic force, a way for the cosmos to ensure the continued flowering of consciousness and complexity beyond the death of its original home. The end of our universe would no longer be a full stop, but a semicolon in an endless sentence of creation. Yet before any of this can be more than a dream, we must first confront the staggering, almost paralyzing scale of time that lies ahead. Human history shrinks to an invisible dot on this cosmic clock. We measure our civilization in millennia, but the future of the universe is counted in years that require new languages of mathematics to even write down. This is a journey into deep time, a scale so immense it redefines our understanding of temporary and permanent. The era we live in right now, the Age of Stars, is known as the Stelliferous Era. It is a brilliant but fleeting fireworks display. It will last for perhaps 100 trillion years, a number that already feels abstract, but that is just the opening act. When the last red dwarf star finally winks out, the degenerate era begins. For 10 to the 40 years, the cosmos will be a graveyard of fading embers, populated by the cold, dark remnants of stars, white dwarfs and neutron stars slowly cooling in the dark. That number, 10 to the 40, is a 1 followed by 40 zeros. To grasp it, consider that the entire current age of our universe is only about 10 to the 10 years. The degenerate era is a period a trillion times longer than everything that has come before. And still, this is not the end. When the last black hole evaporates via Hawking radiation, we enter the black hole era, a dominion of darkness that could persist until 10 to the 100 years from now. This timespan has a name, a googol. It is a number so vast that there are not enough atoms in the entire observable universe to count to it. If we were to write it out, it would be a 1 followed by 100 zeros, a numeral that would stretch across your screen. If protons decay, as many theories predict, what follows is the dark era, a near-featureless void where all complex matter has dissolved. And if the universe persists long enough, we enter the realm of the truly bizarre, an epoch of quantum fluctuations lasting for 10 to the 50 years or more. This is not a number you can write down. It is an exponential tower of such staggering height that the entire googol seems infinitesimal by comparison. On these timescales, the impossible becomes inevitable. A perfect statue could randomly assemble from drifting dust, or a fully formed brain could spontaneously pop into existence from the quantum foam, a Boltzmann brain with false memories of a life that never was. Our entire cosmos, from its fiery birth to its cold demise, is just a brief flicker of structure and light in an otherwise endless, silent night. How can any mind possibly comprehend a duration that makes a googol years seem short? We are forced to abandon numbers and turn instead to the power of story. Robert Frost's simple choice between fire and ice resonates because it touches a deep truth about finality. The fire of a big rip or a big crunch speaks to our fear of a violent, sudden end, a cosmic conflagration where everything is consumed. The ice, however, is different. It is the slow, patient cold of the heat death, a quiet and inexorable fade into stillness that feels, in its own way, even more absolute. We find these themes echoed across cultures and centuries, from visions of apocalypse to the serene, cyclic imagery of a cosmic egg, cracking open to give birth to a new reality from the shell of the old. These are not mere decorations. They are essential tools for the human mind, allowing us to wrap our consciousness around ideas that would otherwise be too vast and terrifying to hold. A universe as a clock winding down gives us a framework for entropy. A story reaching its final page makes the end of time feel narrative and complete. A candle burning out captures the intimate tragedy of a finite energy supply. Each metaphor illuminates a different facet of the end, transforming abstract physics into something we can almost feel. They bridge the chasm between the cosmic and the personal, letting the fate of galaxies ripple through our own sense of mortality. When we say the universe might end in ice, we are not just describing a thermodynamic equilibrium. We are giving voice to a profound human anxiety about silence, about stillness, about a future so vast and empty that it echoes. These stories we tell about the end are, in the end, stories we tell about ourselves and our fleeting, brilliant moment in the light. What does it mean to find meaning in a cosmos that appears to have an expiration date? This cosmic expiration date does not invalidate our brief, brilliant moment of existence. It frames it. If the universe and all its grand structures are destined to fade into nothingness, does that render our lives, our art, and our love meaningless? The existentialist philosopher Jean-Paul Sartre proposed a radical answer. He argued that the absence of any pre-written, eternal cosmic purpose is not a void to be filled with despair, but a terrifying and liberating freedom. With no divine script or final scorecard, the responsibility for creating meaning falls entirely on us. We are the authors of our own value, the architects of our own purpose, right here and now. This very transience, the fact that nothing lasts, is what gives our experiences their poignant beauty and urgency. The cherry blossom is cherished precisely because its bloom is fleeting. A song is moving because its final note will fade into silence. Our temporary consciousness becomes not a flaw in the universe, but its most exquisite feature. This perspective resonates through wisdom traditions across the globe, from the Buddhist concept of impermanence to the Latin reminder that we are mortal, so we should live. The knowledge of an ultimate end can also be a profound equalizer. It reminds us that every human, every creature, every star is part of the same magnificent and tragic story of emergence and dissolution. We are all stardust, and to stardust we will all return. This realization can forge a powerful sense of cosmic connection, a shared fragility that dissolves artificial boundaries and inspires a deep responsibility to cherish this rare gift of awareness. Our brief flicker of consciousness is a chance to witness the universe, to feel, to create, and to love. The final fate of the cosmos invites us to ask the most fundamental question of all. What does it mean to be a self-aware part of a story so much larger than ourselves? Long before telescopes peered into the void, humanity looked inward and upward, weaving stories to explain the terrifying beauty of existence. The Norse people envisioned Ragnarok, a final, frigid winter giving way to a cataclysmic battle where gods and monsters would perish, and the world itself would be consumed by fire and water, only to rise again, green and fertile from the sea. This was not a final end, but a violent reset. In the ancient traditions of Hinduism, time itself is cyclical, an endless breath of the cosmos. For eons, the god Brahma creates the universe, Vishnu preserves it, and Shiva ultimately dissolves it in a great pralaya, a cosmic night that precedes a new dawn of creation. This is a universe that dies and is reborn over and over for all eternity. In stark contrast, the Abrahamic faiths of Judaism, Christianity, and Islam envision a linear history, a story with a single divine beginning and a definitive apocalyptic end. This finale is not a random dissolution but a purposeful culmination, often involving a final judgment, the resurrection of the dead, and the establishment of a perfect, everlasting kingdom. A world made new not through repetition but through a final, righteous transformation. These myths, whether cyclical or linear, all serve a profound human need. They are not primitive failures of understanding, but brilliant, imaginative frameworks designed to answer the same questions that keep cosmologists awake at night. Why is there something rather than nothing? Where did we come from? And where, in the end, are we all going? Our modern scientific epic, with its dark energy and proton decay, is the newest chapter in this ancient, universal human endeavor. It is a different language describing the same profound mystery. Science and myth are not adversaries. They are fellow travelers on a journey to comprehend the greatest story ever told, each offering a unique lens on our collective search for meaning in the face of the infinite. Our scientific forecast for the end of all things rests on a fragile foundation, the assumption that the laws of physics we observe today remain unchanging and absolute across trillions upon trillions of years. This is the fundamental line separating established cosmology from theoretical speculation. A prediction like the heat death is built upon the bedrock of thermodynamics and general relativity, principles tested and verified in labs and observatories across our cosmic neighborhood. We watch stars cool and systems run down, and we extrapolate that universal trend to its ultimate conclusion. The mathematics is clear, and the observational evidence, from the expanding universe to the cosmic microwave background, strongly supports this broad, cold trajectory. But when we venture into the territory of the Big Rip or vacuum decay, we step onto much thinner ice. these scenarios depend not on the laws as we know them, but on hypothetical extensions of those laws. They require the existence of phantom energy, a substance never observed, or a precarious instability in the vacuum of space that has never been detected. These are not wild guesses, they are logical possibilities that emerge when we push our most ambitious theories to their mathematical limits. Yet the very timescales involved create an insurmountable barrier. We cannot run an experiment that lasts a googol years to see if a proton truly decays. We cannot create a universe in a lab to watch its final moments. This forces cosmology into a unique and philosophically charged position. It is a science that must extrapolate from a single data point, our observable universe, and project its history forward into realms of time and energy that are, by their very nature, beyond any direct human experience. This process is not a failure of the scientific method, but one of its greatest strengths, being transparent about the uncertainty, about the line between what is well supported and what is possible, defines the very frontier of knowledge. It tells us where our models are robust and where they become fragile, guiding the questions that will drive the next generation of telescopes and experiments. The ultimate fate of the cosmos may forever lie just beyond the horizon of absolute confirmation, a permanent and profound mystery. This inherent uncertainty, however, does not leave us with nothing. It invites us to consider that the reality of the end may be stranger and more wonderful than any of our current theories can describe. Our universe might be a single page in an infinite book. This is the vision offered by string theory, where the most fundamental pieces of reality are not tiny dots, but unimaginably small, vibrating loops of energy. Think of an electron not as a featureless point, but as a minuscule string, so small that if an atom were the size of our solar system, the string would be no larger than a tree on Earth. The pitch and rhythm of a string's vibration determine what kind of particle it becomes. Much like different vibrations of a guitar string create different musical notes. One vibration pattern gives us an electron, another a quark, and another the particle of light itself, the photon. In this symphony of strings, all the forces and particles of nature are unified into a single, elegant composition. But this beautiful theory requires a drastic reimagining of space itself. For the mathematics to work, the universe must have more than the three spatial dimensions we experience. String theory suggests there are at least 6 extra dimensions, all curled up into a geometry so tiny and complex that they are completely hidden from our view. It is as if we are ants crawling along a vast, undulating landscape, utterly unaware that every single point we touch is actually a tightly wound, 6-dimensional labyrinth. This radical framework opens the door to an even more astounding possibility, that our entire 3-dimensional universe is just a membrane or a brane, adrift within a much larger, higher-dimensional reality called the bulk. We are not merely in this higher-dimensional space, we are stuck to a surface within it, like characters living on the 2-dimensional surface of a page, unable to perceive the full volume of the book. This concept of a brane world completely reframes the origin of everything. What if the Big Bang was not a singularity, but a collision? This is the core of the ekpyrotic universe model, developed by physicists Paul Steinhardt and Neil Turok. In their cyclic vision, our 3-dimensional brane floats in the bulk, parallel to another brane. The 2 membranes are drawn together by an invisible force, eventually smashing into one another. The colossal energy of that collision did not create matter and energy from nothing, but rather ignited the hot, dense state we call the Big Bang, setting our cosmic page ablaze with light and matter. Our universe then expands and evolves just as we observe, but here is where the story diverges. Instead of expanding forever into cold darkness or collapsing into a fiery crunch, the attraction between the branes pulls them together once more. The end of our universe is not a finale but an intermission. The next collision resets the cosmic clock, beginning a new cycle of expansion and evolution. This process repeats potentially forever, with each cycle lasting perhaps 1 trillion years. In this model, there is no true beginning and no absolute end, only an endless, rhythmic dance of creation through contact. The universe avoids the infinitely dense singularity of a traditional Big Crunch because the branes simply bounce off each other, their hidden extra dimensions providing a cosmic cushion. This grand cycle suggests that the very concept of an end might be a limitation of our three-dimensional perspective. Our entire cosmic history, from the first stars to the last black hole, could be just one act in a play with an infinite number of encores, a story without a final page. Yet the very idea of an end rests on a profound assumption that the universe is a linear story with a final page. What if that assumption is wrong? We once entertained a vision of a cosmos without beginning or end, a perfect steady-state universe. In this model, the universe was eternal, its large-scale appearance unchanging over time. To account for the observed expansion, the theory proposed that new matter was continuously created to fill the voids left by receding galaxies, maintaining a constant density forever. It was an elegant, philosophically comforting idea, a universe that simply was, always and forever. But this model could not survive the evidence. The discovery of the cosmic microwave background, that fossilized glow from the universe's hot, dense youth, was a death knell for the pure steady-state theory. It proved the universe had a dramatic beginning, a moment of origin that the steady-state model could not accommodate. Yet the philosophical allure of an eternal cosmos never truly faded. It simply transformed. The concept of eternal inflation revives this idea on a far grander scale. Imagine a meta-universe, a vast, seething background of spacetime that is forever expanding at an explosive rate. Within this inflating bulk, pockets like our own universe continuously pop into existence, each with its own unique physical laws and its own finite timeline. Our entire cosmic history, from the Big Bang to the final black hole, is just a local event within one of these bubbles. While our pocket universe may have a beginning and an end, the greater multiverse that spawned it has always existed and will always exist, endlessly giving birth to new realities. In this picture, asking for the final fate of the universe is like a single wave in the ocean asking for the final fate of the sea. The question becomes almost meaningless, confined to our local bubble. This perspective is further radicalized by certain interpretations of quantum mechanics. The many worlds interpretation suggests that every quantum decision, every possible outcome of every event, is realized in a branching, ever-diverging web of parallel universes. In this view, there is no single end to reality. There are only endless forks in an infinite road. For every universe that ends in a heat death, another might avoid it. For every civilization that faces the final darkness, another finds a way to escape. The narrative of reality is not a linear story with one climax and conclusion, but an impossibly complex, ever-unfolding tapestry where every possibility is woven into the whole. This shifts our focus from a single, predetermined destiny to a spectrum of potentialities. It suggests that the only true constant across the vastness of existence is not stillness, but perpetual change and unending variation. As we gather these disparate threads, from the cold equations of thermodynamics to the dizzying possibilities of the multiverse, we are left to weave them into a single, coherent picture of what may ultimately await us all. So the cosmic dice appear to be loaded in favor of a quiet fade. When we bring all the evidence together, From the geometry of the cosmos to the whisper of the quantum vacuum, one scenario stands as the most probable forecast. The universe is extraordinarily flat, a condition measured with stunning precision by the Planck satellite. This flatness tells us the density of the cosmos is very close to a critical value, which means there simply is not enough matter for gravity to ever reverse the expansion and pull everything back. The dream of a cyclical big crunch, while beautiful, is almost certainly not our destiny. The true arbiter of our fate, dark energy, also seems to be playing a consistent hand. Its equation of state parameter, W, is measured to be incredibly close to -1. This value acts as a signature for a constant, unchanging force, directly opposing the runaway phantom energy required for a catastrophic big rip. As for the quantum threat of vacuum decay, our most detailed studies of the Higgs field, the entity that gives particles their mass, suggest it is probably in a stable state, not a precarious false vacuum poised to collapse. This collective evidence points overwhelmingly toward the long, slow farewell of the heat death. It is the standard model of cosmic demise, the most conservative and well-supported extrapolation of the laws of physics as we understand them. Yet this synthesis is a snapshot, not a final verdict. It is the best answer we have with the data available today, a map drawn from our single point of observation in an immense and ancient cosmos. Every new telescope, every deeper observation, holds the potential to refine these numbers, to shift the probabilities, and to reveal a universe more dynamic and surprising than we ever anticipated. This brings us to the final and perhaps most important question. Why does this knowledge of a cold, distant end, trillions upon trillions of years in the future, matter to us here and now? This cosmic forecast for a cold, dark end is not a reason for despair, but a profound source of meaning. The very fact that the universe has an expiration date, however distant, makes our fleeting moment of awareness impossibly precious. We are not accidental tourists in an eternal, unchanging landscape. We are witnesses to a brilliant, temporary flourishing of light and complexity, a brief window in cosmic time where the universe is both habitable and transparent enough to be understood. Our existence is a statistical miracle against impossible odds, a spark of consciousness in the vast, indifferent dark, and it is our unique privilege to be the universe itself becoming aware, looking out and deciphering its own grand and tragic story. This knowledge forges a powerful bond of shared destiny. Every human being, every creature on this pale blue dot, is a fellow traveler on the same incredible journey from stardust to stardust. The arbitrary lines we draw between nations, cultures, and individuals vanish against the backdrop of our common cosmic origin and our collective cosmic fate. We are all in this together, adrift on a fragile spaceship Earth, and the responsibility to cherish this brief gift falls upon all of us. To study the end of all things is not an act of morbid obsession. It is one of humanity's most courageous and beautiful endeavors. It is a celebration of our insatiable curiosity, a testament to the power of a fragile mind to reach across the void and grasp the destiny of the entire cosmos. This journey of understanding, from the first questions asked around an ancient fire to the data streaming from our mightiest telescopes, is not just about how the story ends. It is about the profound truth that we are here to tell the story at all. Our cosmic forecast is a masterpiece of inference, yet it rests on foundations of profound ignorance. We have mapped the journey from a fiery beginning to a cold, dark end, but we must now confess that the most fundamental questions remain wide open. We do not truly know what dark energy is, only what it does. We lack a complete theory that marries the vast cosmos of general relativity with the tiny quantum world. We have never seen a proton decay, so we cannot be certain all matter will eventually dissolve. And we have no idea if our universe is a solitary existence or one bubble in an infinite, frothing multiverse. These are not minor gaps, they are chasms in our understanding, and the bridges across them are built from future experiments. The next generation of discovery is already taking shape. We will push the Hubble Space Telescope's legacy further with the Nancy Grace Roman Space Telescope and the European Space Agency's Euclid Observatory, creating three-dimensional maps of the cosmos to measure dark energies push with razor-sharp precision. We will listen for the faintest whisper from the cosmic dark ages, a hydrogen signature known as the 21-centimeter line, which could reveal the universe's conditions before the first stars ever ignited. We are building ever more sensitive gravitational wave detectors, like the Laser Interferometer Space Antenna, or LISA, designed to sense the ripples from the universe's very first moments, a time currently hidden from our view. On Earth, particle colliders will continue their search for physics beyond the standard model, hunting for new particles or forces that could completely rewrite our models of cosmic evolution. The story of the end is not a finished book sitting on a shelf. It is a manuscript with blank pages, and we are the ones holding the pen. Every new data point from a telescope, every unexpected signal from a particle collision, could be the clue that overturns our expectations and reveals a finale far stranger than any we have yet conceived. This relentless, uncertain quest is the engine of science itself. It drives us to build better machines, to ask deeper questions, and to push the very boundaries of what is knowable. Our curiosity about the ultimate fate of everything is not just a search for an answer. It is a celebration of the human spirit's need to look into the darkness and demand to know what lies there. From the silent freeze of heat death to the violent tear of the Big Rip, our journey across cosmic endings reveals a profound truth. The leading forecast, supported by our best observations, points to a long, slow fading into darkness, a final equilibrium where the universe achieves a perfect, uniform stillness. Yet this scientific conclusion is not a reason for despair. It is a powerful reminder of the incredible, fleeting beauty of the cosmic drama in which we are all participating. In this grand narrative, our existence becomes a brilliant, temporary spark against an unimaginably vast and ancient canvas. The astronomer Carl Sagan captured this perfectly when he reflected that we are a way for the cosmos to know itself. Our ability to look up at the stars, to trace the history of galaxies, and to ponder the ultimate fate of everything is a triumph of the human mind. It is the universe awakening to its own story. Let this exploration inspire in you a deeper wonder for the cosmos and a renewed commitment to cherishing our brief, precious moment within it. The story of the cosmos is inescapably our own story, and it is still being written. Thank you for joining this contemplation of eternity. If these ideas resonated with you, we would love to hear your thoughts in the comments. And for more journeys to the edge of understanding, be sure to subscribe.